if you are an ordinary level student and you have your board exams coming soon, your board exams could be your GC ordinary level, it could be your WAEC and so on, and you're a physics student and you do not want to fail the physics, but you rather want a platform that can help you to achieve your dreams of scoring as many A grades as possible in physics, chemistry, mathematics, further additional mathematics, and so on, geography, economics, and so on, then you're watching the right videos today, because in this video we shall be looking at the correction of the ordinary level physics in the GCE 2020, the either question. So stay tuned, because we shall be highlighting all the possible answers to which they can suit this particular question, and by the end of this video we shall be able to answer the question so well and be able to attempt the rest. But I'm going to help all of you guys to pass all your exams in a good place, but I can only do so if and only if you subscribe to my channel and you follow my Facebook page, which I shall have all that in the description below. And the most importantly, don't forget that you can only watch the next section of this video if you are a subscriber. Okay, so just head over and press the subscribe button and give this video a like, so that it's going to motivate me to produce more and more content for you guys. Okay, and I'm going to do so for you guys. So let's dive straight into it. Okay, now as you can see, this is the question 7. They said you should answer all questions, choosing one question from each pair of alternatives. So in this video today, we shall be looking at the question 7 as the question 7 either. Then the next video now we'll look at question 7 or. So this question 7a, woman 1 is saying that we should state 2 reasons why some solids float in water while others sink in water. Now, then the woman 2 is talking about the experiment. Now, should describe an experiment to determine the density of a piece of iron, and your account should include all of these stuffs. And the woman 3 says that we should name one use of a solid with a high density and a low density. Then these other questions follow. So I'll just keep the book aside and let's work it out. Let's work it out and see how far we can go with it. Yeah, so as we've all seen initially, the equation is asking us to state two reasons why some solids float in water while others do not. All right, let's get started. Let's get started. We'll say in water, solids. We'll start by saying that that I hope you guys can see. Cool. We'll start by saying that solids whose densities are bigger than that of water will sink. Cool. That's the reason. So solids whose densities are more than that of water obviously are going to sink. Then we say that solids whose densities are smaller, oh, I don't know if you guys can see from there, are smaller than that of water will float. Yeah, so if the density of a solid is more than that of water, it sinks, and if it is less than, it floats. Good. So the next part of the equation now is asking us to describe an experiment for which we can determine the density of a piece of iron. Alright, so let's see. Okay, and the question wants us that that we should include an experimental setup, a list of requirements, a list of required apparatus, then the procedure to follow, the measurement to be made, how to obtain a conclusion from the measurement. So let's start with the first one. Let's start with an experimental setup. Now we need to know that, or better still, we can start with the apparatus or the requirements. So let's start with the requirements. Let's start with our requirements. Let's start with the requirements and see.
Okay, so the first requirement in which we are going to need a measuring cylinder. That's the first thing which we'll need. We are going to need a measuring cylinder. Because the measuring cylinder helps us to measure the volume of the quantity we want to measure. Then the next we're going to need a scale balance so that we can get the mass of the iron. We need a scale balance. Then we need the piece of stone, water, and the string. So we need water. Then we need a string so that we can lower the object in the water which is contained in the cylinder. A string. Then we need what? We need a rope so that we could lower it down. Then we need the piece of stone. Yeah, so these are some of the requirements that we need. So let's see if we can sketch the setup. So the setup is going to comprise of a cylinder. So this is how we can sketch a cylinder. I'll just sketch. Note that in physics has no diagram quality. As far as your diagram has all the quantities you're to measure well indicated, you are going to have the mark. Okay. Yes, and know that in physics, diagram is just 2 marks for experiments. It's just 2 marks, and since it's a cylinder, it does have some graduations in it, right? There are some graduations that you shouldn't forget to indicate. Yes, I think this is enough. Yeah, it's enough like this. Then you can put some labelings in it, right? Then you can indicate the water level like this. You can put the water level like this. Let's just see that this is the water level. All right, then we can put this, then we can label it and call it the water. This is how the thing can be ending. Yes, so it also labels from here. Yeah, so this is how we can sketch it. Then we can label here and say that here is what the water. Yes, here is the water. Then the jar itself is what the cylinder, the measuring cylinder. Great. So the question now wants us to describe an experiment to determine the density of a piece of iron, and our account should include the list of what I listed. So in place of this stone here, all we should be saying is what? Iron, not stone, please. Iron. All right, good. So let's start now. So this is the diagram. Okay, this is the diagram and this is the labeling. We've labeled the diagram. We can call this the base, which is not too important. This is the base. Yes, that's the base. So this is how we can describe the experiment. Please, I will not be writing everything here. We can, after listing out the requirements we need, then this is now the diagram of the setup. Then we can now proceed now to start with the procedure to explain how we can go about with the experiment to determine the density. Keep in mind that density is mass over volume. Yes. So this is the experimental setup. Okay, this is it. Then the procedure now, after you must have lowered the piece of iron, after you must have lowered the piece of iron into it, now our new diagram now is going to translate into this. This is how our new diagram is going to be. Please, it is in the procedure. This is how our new diagram is going to be now. This is how the new diagram is going to be, where we have the cylinder. Then we consider here, this is the iron. We don't know the shape of the iron yet. They've not told us. Then this is the rope, which is being used to lower the iron down the water. This is the measuring cylinder. These are the graduations. Good. So this is how our diagram is going to be now. So this is now the stone. Yeah, so this is the stone. This is the stone. I don't know if it's visible. This is the stone. Then this is the water. So let's just assume that let's just say that this initially, right, the volume of this water here was, let's say, V1. Then finally, after lowering the stone inside, the volume of the water rises to a certain level called V2. Good. This is the water. This is the water. So that's it. So you discover that if you understand the experiment and you just draw the diagram, you will be much more able to describe it, because everything is understandable at this point in time. So this is what we have. So we can now call this the string. This is the string. Yeah, this is the string. Good. So if we want to describe now the experiment, we can now start with the procedure. We'll then say that the ion of mass m is weighed using the measuring using a scale balance. Like we'll take the ion and we'll put on the scale balance to get its mass. We can call that mass m. Please, I'll not be writing the procedures here. I'll not be writing them. You can be pausing the videos and writing it out. Yes. So the ion of mass m is being weighed using a measuring cylinder. Now good. And the mass is being recorded as m, which is in kilograms or in grams. Then at the end of the day, now you can convert from grams to kilograms. Good. The mass is being measured. The mass is measured using the scale balance, of which the scale balance here was one of the requirements in which we listed. So it's measured using the scale balance, and its mass m is determined. Now the cylinder is being filled with water up to a certain level. It is not filled to the brim. Take note. It is not filled to the brim. It is being filled up to a certain level, which we can call the volume of water in the cylinder. We can call it V1. It is carefully filled up to a certain level called V1, the level of the volume of water in the cylinder. It is labeled as V1. Good. Then the stone now is the ion is being tied to the string and gently lowered into the water, such that the new volume of the water now rises up to a certain level called V2. It rises up to a certain level called V2. And keep in mind that this V2 is greater than V1. Yes. So you gently lower the stone into the cylinder contained, which contains the water, so that the volume of the water now rises from V1 to V2. Good. Then we record the value of V1. So we record the value of V1 and V2. So we record V1 and V2. Good. After recording our V1 and V2 now, we simply take their difference. We simply take V2 minus V1, and we can call that delta V. That's the change in V, the change in volume. So this is all about the procedure. You first of all fill the cylinder with water up to a certain level, and it should not be to the brim. It should not get full. Okay, it should not get full. It should reach a certain level. You can call that V1. Then you gently lower the ion inside, such that the volume of water now is going to rise from V1 to V2. Then you now take the difference in the volume, that's V2 minus V1, which is going to give you a certain value. You can call that delta V. Good. So that's all about the experiment. Now the calculations. Now we can see that the mass of the water is m, and the initial volume of water is V1, final is V2, change in volume, that's V2 minus V1 is given as what? Delta V. That's the calculation. Good. Then the method in which you are now going to get the density of the water in which the density of the ion in which you are looking for. We know that density, we can abbreviate it as what? As raw, which is equal to what? Mass per unit what? Volume. And the mass of the water was what you calculated in it, is what you got initially, because initially we placed the ion on a scale balance, right? And we measured and we got the mass of the ion, and we called that m. So the density now is going to be what? This m, all that on what? All about the change in volume, not V1 or V2, but V2 minus V1, which is going to what? Delta V. So this is how we can get the density of the ion. So that's the calculation. Now the precaution. What do we say about precaution? The precaution is that we should not fill the water initially such that it gets to the brim, because when the water gets to the brim, if you lower this stone down, you see that what? Part of the water is going to fall to the ground, and that is going to reduce the level of accuracy in the experiment. It's going to give you faulty results. Okay, it will give you faulty results. And the next precaution, when reading these values on the cylinder, make sure you place your eye at 90 degrees, such that you are going to read accurate values. Because if you place your eye at angles, you will see that there's going to be some experimental errors in reading the values from the measuring cylinder. So always try to place your eye at 90 degrees, such that you are going to get accurate values from the measuring cylinder. Yeah, so that was all about the experiment. That was all about it. And these are one of those cheap experiments that you can always describe conveniently. Yeah, so let's move to the next part. So the next part is simply saying that we should name one use of a solid with a high density. We should name one use of a solid with high density. Now the first use is that high density materials, well, we can give examples like lead, are used in gamma radiation shield. Yes, like during radioactive processes, they are being used in gamma radiation shield. So can write and say that high, please abbreviate, high density materials like lead are used for gamma radiation shields. So the next one, this is the use of a high density material. High. Now, the use for a low density material, we can say that low density materials are used in making the framework of aircrafts. Good. So low density materials are used in making the framework of aircraft, boats, ships. Because if an aircraft or an aeroplane or a ship is being built using a material whose density is very high, it's going to cause the ship to sink, and it's going to cause the plane to crash. Yes, so that's how we can answer that question. So let me just turn to the next sleeve and we move to the next. So the next part of the equation now, they are saying that in figure 4, the bulb is suspended from a rubber band such that the system is stable. This is exactly what we have. So that they're asking us a number of questions. So okay, so they want us to copy the diagram and show two forces acting on the system. Oh my God, this is so easy. So this is how we are going to do it. We're just going to indicate here that this is the bulb and this is the rubber. So we know that this the weight of the bulb, right? This is the weight of the bulb. We label it the weight or the gravitational force. Then up we have what? We have the tension force. We can call it the tension force. Okay, tension force is acting. So these are the two forces that we can indicate. Then the Roman 2 is asking us to name the forms of energy possessed by the rubber band and the bulb. So the rubber band contains what? It possesses elastic potential energy. Okay, it possesses elastic potential energy. So the rubber band possesses elastic potential energy. Then the bulb possesses what? Possesses gravitational potential energy. Good. So that's it. Then the Roman 3, they are asking us that do all elastic materials obey Hooke's law? Justify with examples. No. The first answer. Okay, so the answer is no. Not all materials obey Hooke's law. So the first answer is no. That's it. No, not all materials obey Hooke's law. We can take, for instance, example. The common example that we should give is what? A rubber. The extension of the rubber is not proportional to the applied force. That's the explanation. The extension is not proportional to the applied force, because if you want to draw the force extension curve, you see that it is not a complete straight line. It is at the start it's a straight line, but at some point it is no longer a straight line. So that's all about the first part of the equation. Then the next one is saying that figure 5 shows a velocity time graph. I'll just sketch it a bit. This is a VT time graph. So this is a graph in which you have been provided, and they want us to describe the motion of the graph from the section OA. We should describe the motion in a section OA and section AB. Now this is a velocity time graph. So the motion of the car from A to B, we can see that from A to B, the car is doing what? The car is accelerating. The car is accelerating at a constant rate. So from A to B, the car is accelerating. Yeah, so the car is accelerating. That's from the section O to A. The car is accelerating uniformly from rest. Uniformly from rest. Yes, cool. Then from the section AB, the car maintains a constant velocity. Car maintains a constant velocity. A constant velocity. Yes. So those are the things in which you can see. And the Roman 2 says that we should calculate the distance covered by the car from the first 20 seconds. You should note that the area under a velocity time graph tells you the area covered by the area under a VT time graph tells you the distance. So this total area here just tells me what the distance traveled. So to get the area, I see that this is a trapezium, right? And the area of a trapezium A, which is given as what? Half sum of parallel sides. These are the parallel sides. So I'm going to have half sum of from 0 to 20. This is 20 plus the distance from here to here. That's 20 minus 10, which gives me what? 10 times the height. The height is 5. So this is going to be 20. Okay, so this is going to die down into 20 plus 10 is 30, right? 30 on 2 gives us what? 15. 15 times 5 gives us 75. So the distance traveled is 75 meters. Wait, so that is it for this particular section, and hope to see you in the next section.
Thank you very much guys for watching, and as always, you can only watch the next video if you're a subscriber to our channel. So guys, please hit the subscribe button and like this video, share that with your friends so that you can have access to watch the next video. And don't be stingy, like I said guys, share the video so that we can have so many subscribers to join us, and we're going to progress in that same light. Remember, no student that has been watching all my videos are going to fail the exam for whatever reason. So guys, watch out for the next video and subscribe to our channel and have access to all our content. Thank you.